Good morning, friends. Up till now, in the last session, we have discussed about the shear force and bending moment diagram. So please recall something about shear force and bending moment diagram, that what we proceed up till now in the previous session. In the previous session, we were discussed about what is shear force, what is bending moment, and how to plot the shear force diagram as well as the bending moment diagram for a simply supported beam, cantilever beam and overhanging beam. So for today's session, we are going ahead the relationship between shear force and bending moment diagram. Before we proceed further, let us be discussed that what we studied up till now in the previous session. So after this session, we will able to describe the shear force and bending moment. Obviously, we can able to plot the shear force and bending moment for overhanging beam, and the today's main objective is to study the relation between the shear force and bending moment. Let us revise. What is the shear force? What is bending moment? When a beam is loaded by forces or couples, stresses and strains are created throughout the interior of the beam. These internal quantities are shear force and bending moment. Please refer this particular figure. Here the beam which has been given to us with the subjected to the external loadings in terms of the point load, maybe the uniformly varying load, maybe in terms of the couple or moment. Now let us divide this particular given beam into two parts, left part and right part, and let us study the one of the part, left section over here. If we refer this left section, these internal quantities which were developed in terms of this force as well as moment are referred as shear force and bending moment. What is shear force and how the shear force is defined? Shear force is the algebraic sum of all the vertical forces acting to the left or right of the section. Means we have to cut a beam. We have to take either left section or either the right section, and the algebraic sum of all the vertical forces that is acting on that section is referred as shear force. Then how the bending moment is defined? Bending moment is the algebraic sum of all the moment of forces to the left or the right of the section. Means for a given beam we have to divide the beam into the two parts, either left part or the right part. For a left part if we are taking, then the bending moment is the algebraic sum of all the moment of the forces. What is the sign conventions that we have been used up till now for shear force and bending moment? Let us make a revise within the minute. So for a beam, if we divide it into the two parts, then this left part, this is a right part. Now for a left part, if the internal force which is acting is of upward sign, or if we are taking a right part and the internal force which is acting out downward, so that internal force referred as shear force as positive shear force. Vice versa, if for a section having a left part, if the force which is acting downward, or for a right part, if a force which is acting upward, this is referred as negative shear force. For bending moment, for a section, if a moment which is acting clockwise for a left section or for a right section, if it is anti-clockwise, this has been referred as positive bending moment. The name of this positive bending moment is referred as sagging bending moment. Or vice versa, for a section, if a moment for a left side is acting anti-clockwise or for a right side if it is acting clockwise, this moment is referred as negative bending moment. As per our sign convention, it is to be told as hogging bending moment. So now let us further proceed for the relationship between bending moment and shear force. Now let us consider a beam subjected to the bending and transverse shear. At some distance along the x direction, further consider a short length delta x. Please refer this particular figure. This is our beam is there. We are taking a section from the left side which is shown over here. This value x is over here, taking from the x. And let us consider a shorter span delta x. So to derive the relation between the shear force and bending moment, let us take the small part of our beam, that is of delta x. Now over this length the bending moment increases by dm and the shear force increases by df. So if you refer this particular figure, so if the force, shear force which is acting at this cross section is of F, then on this section, the another section, the shear force which is acting is F plus delta F. There will be a slightly addition of shear force because of this delta X of the length of the beam. If the M is the moment which is acting at the section A over here, then M plus delta M, that is the bending moment which is acting on the section B over here. So if we take this section out of the beam, we must add the forces and moments that were previously exerted by the material in order to maintain the equilibrium. Please refer the figure once again. This is a one kind of load, external load. Let us assume the uniformly distributed load W which is acting on the short span. So the total load, if I will convert the load in terms of a point load, then the load which is acting on this section delta X is W into delta X. Load multiplied by the distance, total distance on which the load is acting. Let F is the shear force which is acting at the section A and M is the bending moment at the same section, then F plus delta F and M plus delta M are the corresponding values at the end B. In other words, the shear force and bending moment have increased by delta F and delta M respectively. Now, once again the same figure which has already been repeated over here for your reference. Section A is on this side, section B which is on this side. For the section AB in equilibrium, the upward force must be equal to the downward force. In short, we are taking sigma V is equal to 0, that is the equilibrium condition. that is summation of all the vertical forces acting on this system is equated to 0, and assuming as per our sign convention that we had been used since from last series, that is the upward force which is treated as positive and the downward force which is treated as negative, and if we equate it, then F is equal to F plus delta F plus W into delta X. What is this W into delta X? Is nothing but the total downward load which is acting on this section. Now, removing the brackets, if we are removing these brackets, we achieve delta F is equal to minus W into delta X. This is very good correlation which has been achieved over here. Now, in the limiting case, as delta X becomes smaller and approaches to 0, we achieve a relationship that is del df by dx is equal to minus W. Please remember these equations very well. df by dx is equal to minus W. That is, the slope or gradient of the shear force diagram at any point is equal to the load intensity at this particular point. I will repeat these words once again, which having a significance. The slope of the shear force diagram at any point is equal to the load intensity at that particular point. Now, after this derivation, let us we take considering the algebraic sum of all the moments about any point must be 0 for the equilibrium. In short, we are taking the moment about A, that is sigma ma is equal to 0. That equilibrium conditions we are using right now. Sigma is the symbolic representation of summation, m is the moment, and A is the point at which we are interested to take the moment. Means sigma ma is equal to sum of all the moment of forces about point A is equated with 0. Now the question may arise in the mind, how many forces are acting on this system? Please refer the figure. Refer the figure. At section A, the force F which is acting, also the moment m is acting. Here the load which has not been shown, but if you refer the once again the previous figure, here the load which is acting, that is W into delta X, which is also acting, as well as the at B section the moment which is acting m plus delta m, as well as the shear force which is acting on the section B, that is F plus delta F. So if we repeat 1, 2nd, 3rd, 4th and 5th, the 5 forces which is acting on this system. So now we have to take the moment of all the forces at section A. So if we refer that figure, please see this figure very carefully. Then the first is m. As the m is the moment directly given to us, so we do not have to use any kind of perpendicular distance, and the plus sign. The plus sign indicated that the clockwise moment are treated as positive, and the same sign convention which has been adopted from our side since from last series also. The another moment is bracketed sign m plus delta m and the minus sign ahead because the anticlockwise moment which is acting at B, and we do not have to multiply by any distance. Now next load. This W into delta X is nothing but the point load or converted point load which is acting at the CG distance. So this is the force multiplied by the perpendicular distance delta x by 2. So this is the moment generated by a load W, and the moment which is created in terms of clockwise direction, hence stated as positive. Another force F plus delta F into delta x, and this plus sign because creating a clockwise moment. Now let us be understood this sign convention, how plus and minus will come using this tabletop. Please see the figure in the tabletop. This is a small part of our beam. Length is of delta x. This section is A, this section is of B. At this section the force is acting F. At this section the force is acting F plus delta F. The moment is acting M. The moment over here is acting M plus delta M. The load which is acting over here, W, kilonewton per meter. So we are taking the moment over here at A point, sigma ma, which is equated to 0. Then this is clockwise, then the plus m. Another is anti-clockwise, so minus sign, m plus delta m. Another force, that is this one. W is the UDL, kilonewton per meter. So total load is W into delta x. This load which is acting at CG, see the figure over here. This is nothing but W into delta x. This distance is of delta x by 2. So if we are using this load, then it is delta x by 2, and this creates clockwise moment plus sign. Another force, and that is F plus delta F. So F plus delta F into delta x, perpendicular distance, also acting in clockwise direction of plus sign.